At the last lectures, we discussed the basics of describing geometric objects, and now we'll learn how to modify them. We have discussed so far point and shape notions, metrics, coordinates, space and shape dimensions, modeling of curves and surfaces. Now we proceed with transformations of 2D and 3D shapes. The formulations of transformations are based on matrix operations, which we need to briefly revise first. Points in 2D and 3D spaces are represented as a single row or a single column matrix. The object transformations are usually presented in matrix form, so the basic matrix operations are recalled. Matrix is a rectangular table of elements. The horizontal lines in a matrix are called rows, and the vertical lines are called columns. A matrix with m rows and n columns is called an m by n matrix, and m and n are called its dimensions. If two m by n matrices, A and B, are given, we may define their sum, or addition operation, A plus B, as the m by n matrix computed by adding corresponding elements. Other, shown on this line, matrix operations are identity and scalar multiplication. The matrix and its close relative, the determinant, are extremely important concepts in linear algebra, and were first formulated by Sylvester and Cayley. In the scalar multiplication, each element of the matrix A is multiplied by the scalar value C. In the example below, the scalar C equals 2, and A is a 2 by 3 matrix. It is shown at the bottom how to practically multiply each matrix element by this scalar. Multiplication of two matrices is well defined only if the number of columns of the first matrix is the same as the number of rows of the second matrix. If A is m by n matrix, m rows and n columns, and B is an n by p matrix, n rows and p columns, then their product AB is obtained as follows. First, make a dot product of the first row of A by the first column of B, and the result will be the element 1, 1 of the matrix AB. Second, make a dot product of the first row of A by the second column of B, and assign it to the element 1, 2, and so on. For any element ij of AB, take the ith row of A and multiply by the jth column of B. This example shows how to multiply the matrix A 2 by 3 matrix by the matrix B 3 by 2 matrix. It is easy to remember how to do the matrix multiplication by imaging the first matrix as being built out of row vectors and the second matrix as being built out of column vectors, as shown in the slide. Then, the multiplication can be defined by the expression shown below, where in each product, 1 multiplies a row vector capital V1 or capital V2 by a column vector capital V3 or capital V4 by multiplying the corresponding entries and adding up the result. The matrix multiplication is an associative operation. See the top expression. It is also a distributive operation. See the right and left distributivity in the lower expressions. It is important to note that commutativity does not generally hold. That is, given matrices A and B and their product defined, then generally AB does not equal BA. Determinant is a numerical characteristic of a matrix. Remember that the determinant is a number, not a matrix. It is calculated by a recursive procedure on the base of the determinants of a lower size matrix. The minimal size matrix is 2 by 2, and its determinant can be calculated as shown at the bottom. Matrix transpose makes a column vector A into a row vector AT. It looks like a rotation of the matrix by 90 degrees around its main diagonal. Matrix inverse is a different operation only defined for square matrices. A product of the matrix A with its inverse B makes a unit matrix. Now we can learn two-dimensional transformations and their representation in the matrix form. Translation and rotation are Euclidean or linear transformations, which do not change distances. Scaling and shear are in the class of affine transformations, changing distances between points. We will give matrix representations for these operations in so-called homogeneous coordinates. First, let us realize how transformations are used. The obvious answer is to change the position, orientation, and shape of the object. But even more important, that they are used as nodes of an assembly in complex modeling or of a scene graph in computer graphics. The scene graph describes a complex object composed of transformed simple objects, primitives, given in standard positions. For example, at the point 0, 0. The robot shape in the picture is assembled from just two primitives, block and cylinder, using transformations. We will present transformations of points first of all. This helps transform many objects built on the basis of the list of points. Objects that can be built using points as object vertices are straight line segments, polylines, convex and concave polygons. Lines are drawn between ordered points to create more complex forms, called polylines. The same first and last point make a closed polyline or polygon. If it does not intersect itself, it is called a simple polygon. Simple polygons can be convex and non-convex or concave. In a convex polygon, for every pair of points in the polygon, the line between them is fully contained in the polygon. See the bottom left image. Some two points in a concave polygon are joined by a line not fully contained in the polygon. See the bottom right image. There are also special polygons such as triangle, square, and rectangle. Even a circle can be represented by a polygon with some given accuracy. For all shapes based on vertices, we can transform each vertex and thus transform the entire shape. Let us present a circle as a polygon with 15 vertices, and then stretch or scale it along the x-axis, as shown at the bottom. Now we need to understand how such transformations are defined. Translation of points in the xy plane to a new position is done by adding translation amount to the coordinates of the point. In other words, it is a component-wise addition of vectors v and t, where v is a vertex vector shown in the picture and t is a translation vector. In the matrix form, translation is described as a simple addition of vectors v and t. As already mentioned, to move polygons, we just translate vertices and then redraw lines between them. The translation operation preserves distances between vertices and angles between vectors. Stretching or squeezing a shape in x or y direction is a geometric scale operation. It is defined by a scalar multiplication of vector of vertex coordinates. We can also apply different scalars for different coordinate axes, as shown in the slide. In the example, the house is scaled by the factor 1/2 along x-axis and 1/4 along y-axis. In the case then scaling factors are different for x and y, S is not a scalar but a matrix, and scaling is defined by the matrix multiplication. Note that the scale operation does not preserve distances between points or angles between vectors. See, the house increased in size and displaced after the scaling was applied. Rotation is defined about the origin by the angle theta. The positive angle means counterclockwise rotation and is measured from the positive direction of the x-axis. The given expressions define the new coordinates of the point after rotation. The example shows that rotation about the origin changes coordinates of all points including the lower left corner. R sub theta is a matrix of rotation, and the rotation operation can be represented in the matrix form as shown. Rotation and scale were defined relative to the origin. Suppose the object is not centered at origin. These transformations will not produce expected results, because usually we expect rotation and scaling relative to the object center. The solution is move the object to the origin, then scale and/or rotate, then move it back, as it's shown by the example. This requires composition of several successive transformations. It is difficult to compose translation with other operations because it is not defined by the matrix multiplication. To allow for such a composition, special homogeneous coordinates were introduced. The term homogeneous means that these coordinates allow all transformations to be expressed homogeneously and serve for the composition of all transformations using multiplication of 3 by 3 matrices. For a 2D point in homogeneous coordinates, we just add one extra coordinate w. Two sets of homogeneous coordinates x, y, w and x prime, y prime, w prime present the same point if one is a multiply of the other. For example, the same point is defined by different coordinate triples 2, 3, 7 and 6, 9, 21. The second is obtained by multiplying first by 3. This is just an interpretation of homogeneous coordinates in x, y, w space. The point x, y, 1 on the plane w equals 1 corresponds to the line xw, yw, w in space. The point with coordinates x, y here is a point in 2D, to which we added the extra coordinate. For points written in homogeneous coordinates, translation, scaling, and rotation are expressed uniformly or homogeneously in the matrix form. Note that matrices are 3 by 3 for 2D transformations. The main point is that now translation matrix is in the same form as scaling and rotation. Now we are back to the composition of transformations. If we want to rotate a shape around the point P, we need to do several steps. First, move shape to the origin. Second, rotate it around the origin. And then, translate it back to the original position. These can all be described by a single matrix transformation in homogeneous coordinates. This is how we can get the composite transformation matrix by multiplying three matrices, T, R, and T inverse. Similarly, we can get a composite matrix for scaling about an arbitrary point P1. First, move P1 to origin. Second, scale about the origin. Third, translate point back to P1. Compose three transformations into the matrix T as shown. The composition of transformations can work also just to combine a sequence of transformations into a single one, as it's shown here for 4 transformations. First, move P1 to origin. Second, scale about the origin. Third, rotate about the origin. And the last one, translate to P2. The single composite transformation matrix can be obtained by multiplication of 4 individual matrices. The main idea is that an object can have 1000 points, and there are 2 ways to transform it. The first one is multiply 4 times a transformation matrix by 1000 points. That is equal to 4000 matrix multiplications. The second option is multiply matrices once and then multiply the points by the composite matrix. It is equal to 1000 plus 3 matrix multiplications, as shown by the second line. The matrix compositions dramatically reduce computation time for objects transformation. Please remember that you cannot change the order of transformations without changing the result. This example shows translation followed by rotation, rotation followed by translation. The results are not the same. This means transformations are not commutative. This is the full spectrum of so-called affine transformations in 2D. Then parallel lines are preserved, but distances and angles are not preserved. All these transformations can be described by homogeneous matrices. There are two new matrices for shear and reflection transformations. The shear matrix has a non-zero element out the main matrix diagonal, in the first row for the x-axis and in the second row for the y-axis. For example, the shear operation can skew an object to its side as shown in the picture. Squares become parallelograms. X-coordinates skew to the right, while y-coordinates stay the same. The result looks like taking a desk of cards and pushing top to the side. Each card shifts relative to the one below it. Notice that the base of the house at y equals 1 remains horizontal, but shifts to the right. The picture below shows how the skew operation influences the points. See that the points are translated parallel to x-axis. Everything along the line y equals 1 stays on the line y equals 1, but is translated to the right. Distance between points on this line is preserved. A 1D homogeneous coordinate translation looks like a 2D skew transformation. Now we can make a step one dimension higher. First, let us discuss how objects can be defined using objects of lower dimension. Line is drawn by tracing path of a point as it moves. Square drawn by tracing vertices of a line as it moves perpendicularly to itself. Cube drawn by tracing paths of vertices of a square as it moves perpendicularly to itself. Circle drawn by swinging a point at a fixed length around a center point. These operations show that vertices remain important in any dimension. Briefly, 3D objects can be built as surfaces glued together of triangles or quadrangles to make not flat facets, but curly ones. Polynomial spline surfaces can be used. In all these models, vertices are used to carry geometric information and to transform the object. Next, we will cover the following groups of 3D transformations: affine transformations, deformations, set-theoretic operations, metamorphoses. Then, using homogeneous coordinates for 3D points, each point is represented by a vector with 4 elements x, y, z, and 1, and each transformation by 4x4 matrix. In the picture below, a matrix for translation is shown. It's similar to a 3D translation matrix. In three-dimensional space, rotations are made not around points, but around straight lines. Any rotation can be presented by 3 rotations around the coordinate axis x, y, and z. 2 of them are presented in the slide: z-axis rotation and x-axis rotation with the corresponding 4x4 matrices. Scaling has a simple matrix with scaling factors on the main diagonals. This is scaling about the origin. For the scaling about an arbitrary point, one has to apply the same technique as in 2D. First, translate the object to the origin, scale about the origin, and then translate the result back. The composite matrix for this operation is shown below. The above transformations can be called linear because only linear functions are applied to the point coordinates. The next group is nonlinear deformations. Note that two different types of transformations are applied to point depending on the object model. Forward transformations are used for vertices, polylines, parametric curves and surfaces. Inverse transformations are used for implicit curves, surfaces and solids. Twisting is a general form of rotation. You can think of it as a rotation about an axis, with the angle of rotation changing along this axis. It is reflected in the expression for angle theta equals function of z coordinate. Examples show a cube and a teapot twisted. Tapering is a generalization of scaling, where the scaling factor changes along some axis. We can see the examples. The scaling of the teapot and the cube change from the left to the right. The scaling factor r is given as the function f at z. Bending is also kind of nonlinear rotation, with the axis usually orthogonal to the symmetry plane of the object, and the angle of rotation changing between 0 and 180 degrees. At the lower right, we see a composite transformation including tapering, twisting, and bending, applied consequently to a superellipsoid. The above operations change the coordinates of the point. Set-theoretic operations are different as they add or remove points from the object. They are also applied to two arguments, not to one, as the above operations. For example, the union operation includes a point in the result if it belongs at least to one of the initial objects. Intersection selects only common points of two objects. The difference A and B includes points belonging to A and excludes points belonging to B. These operations are illustrated for 2D and 3D objects on the slide. Metamorphosis or morphing, warping, takes one shape and continuously changes it into another shape. There are many problems with this operation applied to polygonal meshes and parametric surfaces or curves. It is hard to handle different number of points in two objects. Changing the topology is an unsolved problem, for example, metamorphosis of a sphere mesh to a sphere with one or more handles. Surface self-intersection are possible. On the other hand, this has quite general description for the implicit form, as we can apply just interpolation between two functions to get the desired result. This is an example of the metamorphosis of implicit surfaces. You can see that the objects can have different topology, such as number of holes. And still, this is handled automatically by the modeling system. But in the case of polygonal meshes, it would crash without any acceptable results. 3D scenes are typically stored in computer graphics in a direct acyclic graph called a scene graph. Typically, scene graph format contains objects, cubes, spheres, cone, polyhedrals, etc., located at the origin, stored as leaves. Transformations are also nodes in scene graph, and other types of information for objects rendering. In this example, only two types of standard primitives are used, block and cylinder. They are transformed at the nodes of the graph and compose to complex object. How is the composition of several transformations implemented using the scene graph? In the scene graph below, transformations are shown in red and objects in green. The transformation T0 will affect all objects below it in the tree, but T2 will only affect object 2 and one instance of group 3. Note that if you want to use multiple instances of a sub-3, such as group 3 above, you must define it before it is used. This example explains how to collect transformations red for each object green in the leaves. For example, for O2, we need to combine transformations M2 and M3 and then apply it to the object. The list of transformations for other objects you can see in the slide. The Book of Foley covers transformations quite well. This book is also a good source of information and illustrations. Some additional references are listed here.